Hello. The third problem which we will be seeing is the application of dynamic programming for solving linear programming problem. Simple problem will be taking for this purpose just containing two variables and two constraints. Maximize z equal to 3x1 plus 4x2 subject to x1 plus x2 less than equal to 60, 2x1 plus 3x2 less than equal to 150, and both the variables x1 and x2 positive greater than equal to 0. So as we have seen in our previous problem, we have to break the problems in various stages. Here there will be only two stages. The first stage will be containing just one variable, consideration of one variable x1, and the other stage will be containing x2 along with x1, right? So let's write our first stage problem with variable x1. Maximize z equal to 3x1 subject to x1 less than equal to b11. Okay, as we have seen in our earlier problems that our right hand side will never be a constant, it will be a variable called as state variable. So x1 less than equal to b11, and from second constraint 2x1 less than equal to b12. Now here we have two state variables because there are two constraints. Per constraint there is going to be one state variable. Okay, so as here there are two constraints, we'll be having two state variables. Now that we have written state variables, it is the turn to declare our alternative variable. So as the case was in our earlier problem, we have the alternative variable for the variable of the stage. Here the variable of the stage is x1, so we will be writing x1, let x1 be u1. Now that we have state variables and we have alternatives, we are in position to write the return function for first stage r1. It is the function of state variables. Now we have two state variables b11 and b12 and one alternative. Okay, so r1 is the function of b11, b12 and u1. Now what you need to do while finding the return function, because we have said x1 equal to u1, you simply put this u1 in the objective function or the return function. So your return function now becomes 3u1. Now in fact u1 will be minimum of b11 and b12 by 2, because it is the value of x1. u1 is the alternative value which we have set for x1, and x1 will in any case be less than or equal to the minimum value of b11 divided by coefficient of x1, that is 1, and b12 divided by the coefficient of x1 in second constant. So it is going to be minimum of b11 comma b12 by 2, right? So right here while writing the return function we have written it 3u1. That's fine. But when we want to write the optimal return for first stage, it is going to be simply the function of state variables b11 and b12 here, because there are two constraints, so two state variables, right? So now your optimal return r1 star must contain only b11 and b12, and that is we will be writing 3 into, because 3 is coming from here, 3 into minimum of b11 comma b12 by 2, just on the basis of explanation just given to you, right? So far clear, I think? Yeah, fine. Now coming on to stage 2, like we had the practice of writing the variables in the order they are getting dealt. Like x2 will be the new variable entering in this stage 2. X1 has already been dealt with in the previous stage. So we are writing our objective function as maximize z equal to 4x2 plus 3x1. Okay. Subject to x2 variable we are writing first, x2 plus x1 less than equal to b21. Even though we know that it is a constant, but for the sake of having state variables, we are writing their variables b21. The first subscript from b21 is telling us the stage number, and second subscript is telling us the constant number. Okay, so x2 plus x1 less than equal to b21, and then another 3x2 from here, 3x2 plus 2x1 less than equal to b22. So here we have two state variables because there are two constraints. And once again you see here that this part on which I am moving the cursor is subset of a big problem of second stage, and this subset is the problem of previous stage. We have already dealt with it in our previous stage, right? So now we having declared the state variables b21 and b22, now we need to have alternative, right? Let x2 be u2. This is a simple declaration for declaring our alternative. Okay, x2 be u2. Now that we have taken u2 for x2, and knowing that the state variables are b21 and b22, we now have to write value of state remaining for previous stage. Now there are two states, right? There will be the value for two states remaining from for previous stage will be now b21 minus u2. This is the value remaining for the first state, b21 minus u2, and second state value remaining for previous stage will be b22 minus 3u2. Clear? This is the value of state remaining for previous stage. Okay. Now we want to find out optimal return from previous stage for value of state remaining for previous stage, right? That is, optimal return for previous stage means r1 star, and value of state remaining for previous stage means b2 for b21 minus u2, that is the first state remaining, and second state b22 minus 3u2. Now from previous stage we know how to get r1 star for the parameters passed b11 and b12. b11 and b12, they are processed like 3 into minimum of b11 as it is, and second parameter divided by 2. So same here, it will be 3 into minimum of b21 minus u2, comma second parameter divided by 2 as was the case above, b22 minus 3u2 by 2. Fine. Now processing this ahead, r2 now, that is the return for this stage we need to find. We have the components for writing return for this stage. First component is, as you see from previous problem, 4 into x2 we are replacing by u2, and for this whole we have found the optimal return for previous stage, that is this one. You simply have to write these two components, add these two components, because our objective function also adds them, right? So it is 4u2 plus 3 into minimum of b21 minus u2. Just on the previous transparency you see b21 minus u2 here, and another component b22 minus 3u2 by 2. Alright. Now optimal return I want to find. optimal return R2 star, it is the function of states only, B21 and B22. It will be simply the maximum value of this two. Okay, maximum of this whole 4u2 plus 3 into minimum of b21 minus u2, b22 minus 3u2 by 2. Now I know b21 is 60 and b22 is 150. So I'll be replacing in this equation b21 and b22 by 60 and 150. That comes like maximum of 4u2 plus 3 into minimum of 60, b21 is 60 minus u2, b22 is 150 minus 3u2 by 2, right? So now having replaced the values of b21 and b22, it is very clear that the R2 optimal totally depends on U2. Okay, U2 is in fact the value of x2. So let us try various alternatives of U2. Important alternatives, not every alternative value of U2. Important, where there is going to be the change in behavior of R2 star. Now one value of u2, as we know that it will always be greater than or equal to 0 because x2 is given to be greater than or equal to 0. So we will be trying to find the value of R2 star when u2 is equal to 0. Okay, this is one important point where I should find the value of R2 star. So I will be putting u2 is equal to 0 in this equation. So it becomes 0 plus 3 into minimum of 60 minus u2 will be 60 and 150 minus 3 u2 divided by 2 will be 75 because u2 is 0. Okay, minimum of this 2 is 60, so 60 into 3 180. So u2 is equal to 0. I have tried. Another important thing where the behavior of this R2 star will change depending upon the change in value of U2 will be when these two components in the minimum bracket becomes equal. After that, probably this component will return the minimum. Right now this component is returning the minimum. So what I will be doing, I will be equating this two and finding the value of u2. At that point I will be finding R2 star, right? So equate R2 star at 60 minus u2 is equal to 150 minus 3 u2 by 2. These two are equal when u2 is equal to 30. So I will be putting u2 is equal to 30 in this equation. What happens? 4 into 30 plus 3 into minimum. Now this both the components are equal and their value is 60 minus 30 is 30 and here also it is 30. So 3 into minimum, 3 into minimum of 30 and 30, that is 30 itself. 30 into 3 90 plus this is 120. This turns out to be 210. This was another important value where I must have found the value of R2 star, that is the optimal return for second stage. When I have tried was at u2 is equal to 0. That always you will have to try. Another value you must try when these two components are equal. That I have got. And third, I must ensure that this bracket minimum always return will be positive because this is the value for previous stage, value of state remaining for previous state. This must not be negative. Okay, so you have to make sure that this will not be less than 0 and this will not be less than 0. Okay, so I put 60 minus u2 is equal to 0. That means u2 cannot be less than 60. And for this 150 minus 3 u2 by 2 less than equal to 0 means I'll be just putting it equal to 0. That gives me u2 will be 150 divided by 3. That is 50. Okay, so in any case u2 cannot go less than 50, because if that happens then this will be if it goes less than 50, for example suppose say it becomes 60, then this will be 0 and this will be negative, and minimum will return negative. That I never want. Written by this function, minimum should always be positive or 0. So that means, that implies that u2 can be maximum 50. It cannot be more than 50. So anyway, I must try this important value. How did I obtain that? By putting once this equal to 0, once this equal to 0, and if there is any other component that also equal to 0, finding u2 by all this, and whichever happens to be least, at that value I want to find R2 star. I hope you have understood it, right? So put u2 is equal to 50 there. So 4 into 50 plus 3 into, I know that this is going to return 0. 3 into 0. Okay, so this returns 200. Okay, this was my attempt to find the maximum here. In another cases, in our previous problem, I used differentiation there because there was no much of a discontinuity in the function. Differentiation is advised when the function is continuous. Okay, here there was no need to differentiate, nor it was possible to differentiate, and there was discontinuity, sort of discontinuity at one point. So I have not, it was not possible in fact to use a differentiation. Anyway, so by comparing R2 optimal at all these 3 points which I have tried, I am finding that R2 optimal is maximum, that is according to my objective function, at u2 is equal to 30, and that is 210. It means that x2 is 30 because x2 is u2, right? Now having got x2, you can obtain x1 directly by putting x2 value in the equations which you are given in the problem, but I won't advise you to do that. What you instead you should do, because this is always the practice, you once after getting x2 or u2, you find the values of states remaining for previous stage. Okay, simply you know that it was b12 minus just b12 minus u2, sorry, b21 minus u2, as you see here, and b22 minus 3u2 by 2. So here it is coming out to be no, value remaining for previous stage is b21 minus u2 and b22 minus 3u2. Okay, b21 is 60 minus u2 is 30, so that I am getting 30, and another value 150 minus 3u2. 150 minus 3u2 means 3u2 means 90. 150 minus 90 gives you gets you 60. So values remaining for state, values of states remaining for previous stage are coming out to be 30 and 60, meaning that b11 and b12, right? These are the values of b11 and b12. And then x1 I need to find, that is equal to u1, and u1 is minimum of b11 and b12 by 2. So that comes equal to 30. This is the formal way as far as dynamic programming is concerned of finding the value of variables of the previous stage. So here I get x1 equal to 30, x2 equal to 30, and z equal to 210. Suppose say there would have been 3 constraints in the problem, and say just the variables would have been 2. Okay, had the variables been 3, we were required to go for third stage, which would have been even more complex than what you see the complexity of the second stage. Okay, you won't have dared to go for third stage. Or say just there would have been just 2 variables and 3 constraints, then you just imagine there would have been 3 components here, because every component is coming from one of the constraints. This is the remaining value of state from previous stage for first constraint, remaining value of state from previous stage for second constraint, and likewise there would have been third constraint. Okay, so you would have tried R2 optimal for U2 equal to 0, that's fine. Okay, but here you were required to try 3 more. Means one intersection you would have taken up first and second component, then second intersection you would have taken up second and third component, and probably third intersection you would have taken up first and third component. Okay, that is going to take away the real ease which is there in other methods. Dynamic programming is not advisable, but just to make you aware of the implementation of dynamic programming for solving linear programming problem, this is the problem, this is the demonstration. Okay, right? So thank you very much. I hope that you have understood it. If not, listen to this video once again. Thank you very much.